So hopefully we're confident with the general equations of simple harmonic motion. There's two specific examples that we have to do. The first one of these is mass spring system, so we're looking at an equation which is to do with the period of a mass on a spring. We need to talk about what factors will affect that, and then we need to look for a specific equation, not the general equations we've done before, just a specific one which will just apply to the situation of hanging a mass on a spring and timing the vibration. So here's our setup. This is just hanging the mass on a spring. So we know that there's a tension from the spring, which I've called T1. We've got a weight down, which is mg. And we know it's in equilibrium, therefore T1 minus mg, the force up, minus the force down, must be equal to 0. But you'll also remember the Hooke's law for the extension of a spring, which is that the force you apply to the spring is K delta L. And we can see from this equation that T1 equals mg, so T1 becomes mg, so mg equals K delta L. That's just hanging the mass on the spring and leaving it alone in equilibrium. But of course we're not going to do that, we're going to stretch it down an extra amount x. When we stretch it down an extra amount x, we get a bigger tension upwards, which I've called T2, but the same force downwards. So we've now got an acceleration, which we know is going to be upwards, so T2 minus mg is ma. This minus sign here has become from the fact that we're measuring the displacement as being positive downwards, but we know the acceleration is going to be upwards. Okay, we also know, again from Hooke's law, that T2 is K delta L plus X. Okay, delta L being the original extension, it's already stretched by delta L. We've stretched it by an extra amount X. But back from here, we know that mg equals K delta L. Okay, so we need to remember that. So to work out the mass times acceleration now, we've got K delta L plus X minus K delta L. Okay, here's our K delta L plus X, but mg I've written as minus K delta L instead because of this. Okay, if we multiply this bracket, you'll see we've got K delta L minus K delta L, so the K delta L's disappear, and we just end it with Kx. Okay, I've swapped the minus sign across there. If we just divide by the mass, we get acceleration equals minus K over m times x. Okay, this is enough to prove it's simple harmonic motion because I've just proved that the acceleration is proportional to the displacement, but in the opposite direction with this minus sign. Okay, we've also shown the two things that affect what this acceleration will be. One is the spring constant, and one is the mass that's on the end of the spring. Okay, so two possible variables we could investigate here, the spring constant and the mass on the spring. Okay, just relating that to our general equation, so this was our general equation relating acceleration to displacement, a equals minus 2 pi f all squared times x. We've just shown that a equals minus k over m times x. So this k over m and 2 pi f squared, this must be the same thing. So 2 pi f all squared is the same thing as k over m. If I just take the square root on the right hand, so on both sides to get rid of the squared, so I get 2 pi f equals root k over m. Divide down by the 2 pi, so I get 1 over 2 pi times root k over m is the frequency. But I wanted an equation to work out the period, so I just invert that equation. T is 1 over f, 1 over 2 pi just becomes 2 pi, and the square root of k over m becomes the square root of m over k. So the formula for any mass oscillating on a spring is that the period of that is 2 pi times the square root of the mass that's on the spring divided by the spring constant. Okay, as you'll see with questions coming up, they tend not to give you the spring constant, they tend to give you what happens when you put the mass on the spring, so you have to work out the spring constant for yourself first for a little bit of sort of synoptic assessment of Unit 2, just in case you've forgotten how to do that. Okay, so here's a few questions, I'm going to work through these. So here's question 1, we've got a 0.5 kilogram mass hung on a spring with a spring constant of 25 newtons per metre. You pull it down, what's the period of the oscillations? Okay, we should be able to do this one hopefully, so we just do, here's our equation, T equals 2 pi root m over k. Here's our mass, 0.5, it's already in kilograms. Here's our spring constant, they've been nice and just given us that number, just put the numbers in your calculator. You should get 0.989 seconds, sorry, so that's a nice straightforward question. Sadly they're not usually that easy. Here's a second one, so now I've got a 0.3 kilogram mass on a spring, it stretches by 0.1 meters. Then you pull it down and release. So we're still using the same equation, but they haven't given us the spring constant. So our first step is to do F equals K delta L to work out the spring constant. The most common mistake here is to put the mass in, but remember this is a weight that we're doing here. So we've got to do the mass times gravity, so 0.3 times 9.8 equals k delta L. We know delta L is 0.1, so just divide there, we get a spring constant of 29.4 newtons per metre. Okay, so you must remember that kind of idea first, before you can then go on to t equals 2 pi written over k. Put the numbers in again. Here's our mass, still 0.3 kilograms. Here's our spring constant. Stick those in your calculator, you get 0.63 seconds for the period. Again, going slightly harder, watchmaker's got a spring with this spring constant. They want to make it oscillate with a period of 0.5 seconds. What mass should you use? Again, still using the same equation, but this time we're trying to find a mass out of here. Okay, so I suggest the best way to do this is do the algebra first, square both sides. So t becomes t squared, 2 pi, all squared becomes 4 times pi squared, m over k. We want the m on its own, so if we multiply it by the k, divide by the 4 pi squared, we get to this expression. Once we've got that, then we just put the numbers in. So 0.1 was the spring constant, times the period, 0.5 squared, divided by 4 pi squared. Okay, that gives you a mass of 6.33 times 10 to the minus 4 kilograms. Okay, or 0.63 grams if you prefer. Okay, last one, they love to do this as well. A mass spring system completes 40 oscillations in 25 seconds. The mass is 0.5. What's the spring constant? So the first step here we've got to do is to work out the period. It's really easy to go the wrong way around here, but you should notice if you've done that. So the period for one oscillation is going to be the total time divided by the number of oscillations, okay, 0.625 seconds. What I'd always recommend you to do is to look at this and think, are these oscillations taking more or less than 1 second? Okay, I've got 40 oscillations in 25 seconds, so clearly that's less than 1 second for each oscillation. If you do this the wrong way up, you'll get more than 1 second. Okay, then we're just back to the same equation again. Okay, square both sides. This time we're trying to get k, so multiply it by k and divide by t squared. Put all the numbers in, and you end up with a spring constant of 50.5 newtons per metre. Okay, don't forget the units, slightly tricky one for spring constant, don't miss those out.